So I am Jyothi Lakshmi from Basic Sciences of Humanities. I am teaching chemistry. In that, the course name is Engineering Chemistry, and the topic today I am dealing with you is electrochemistry. So now I am dealing Unit 2, Electrochemistry. Let us define the term electrochemistry. Electrochemistry is a branch of chemistry which is dealing with the interconversion of electrical energy into chemical energy. So, electrical energy into chemical energy. It means in one process we can convert electrical energy into chemical energy, and chemical energy will be getting converted into electrical energy. So depending on these two processes, we have two different types of cells. So cells are classified into two types. First one, electrolytic cells. Second, galvanic cells. So in the case of the first, electrolytic cell, there is a conversion from electrical energy into chemical energy. It means we are supplying electrical current to undergo changes, and that will be released as the chemical energy. And in the case of the galvanic cell, there is a conversion from the chemical energy into production of electrical energy. So these are the two different processes which are taking place, and we are calling the interconversion of the electrical energy to chemical energy and chemical energy to the electrical energy under a branch of chemistry that is known as electrochemistry. Now we can have the definition of conductor. So conductor is the substance which allows electric current to pass through it. The conductance. So conductance is the amount of electric current passed through the conductor is called conductance. So the units of conductance: ohm inverse. So it is a reciprocal of resistance. Resistance is the restriction of flow of electric current, and this is the flow of electric current which is measured in ohm inverse. So based on electrical conductivity, conductors are divided into two types. First one, electronic conductors or metallic conductors. Second one, electrolytic conductors. So now we'll go ahead with the metallic conductors. So metallic conductors again divided into three types: good conductor, semiconductor, insulators. So good conductors, here the substance which allows electric current easily. So examples: metals like copper, aluminium, iron, etc. Semiconductors here which allows electric current partially. So if you go for the doping, here examples like silicon. If we dope a silicon with the third group element like a boron, the fifth group elements like a phosphorus, then there will be the addition of one electron or a loss of electrons. So that creates the formation of a hole or an electron which can participate in the conducting of electric current. Insulators are the substances which do not conduct electricity. So, rubber, wool, plastics, etc. So, metallic conductors are the conductors which allows the passage of electric current with the flow of electrons. These are divided into three types: good conductor, semiconductors, insulators. So these good conductors are the one which allows the electric current easily in the case of copper, aluminium and iron. Semiconductors which can allow electric current partially like a silicon which conducts the electricity by doping. Insulators do not conduct electric current, rubber, wool and plastics which are not at all participating in the conduction of electricity. Now, electrolytic conductors. The conductors or the substances which can conduct electric current with the flow of ions present in an electrolytic medium. These are again divided into three types: strong electrolytes, weak electrolytes, and non-electrolytes. Strong electrolytes like HCl, NaOH, etc. which can be dissociated completely. So, complete dissociation. Whereas in the case of the weak electrolytes, CH3COOH, NH4OH, partial dissociation takes place. In the case of non-electrolytes, sugar, no dissociation. So, electrolytic conductors allows the electric current to pass through substances due to flow of ions in an electrolytic medium. So, strong electrolytes which undergoes complete dissociation like HCl, NaOH. Weak electrolytes undergo partial dissociation like CH3COOH, NH4OH, ammonium hydroxide and acetic acid. Non-electrolytes like sugar which do not undergo any dissociation and no formation of the ions, so these do not participate in the conduction of electric current. As already we have seen two different types of cells. One is electrolytic cell, another one is the galvanic cell. So here the electrochemical cell is the device which converts chemical energy into electrical energy. So production of electricity takes place in an electrochemical device. So here example of electrochemical cell is galvanic or voltaic or Daniell cell. Now let us see the construction of electrochemical cell. So we have two half cells. This is a salt bridge which maintains the electrical neutrality between two different half cells. So here we have Zn rod and here copper rod. And this is an electrolytic medium in both the half cells. So this is Zn rod, which is an electrolyte immersed in an electrolytic solution, that is ZnSO4. And this is salt bridge. This is copper rod, which is immersed in an electrolytic medium of copper sulfate solution. So these are the aqueous solutions. And these are connected in a circuit. Zinc rod acts as negative electrode, which is known as anode. And this is copper rod is immersed in copper sulfate solution, acts as positive electrode. So this is called as cathode. So zinc rod acts as anode and copper rod acts as cathode. At anode, oxidation takes place. At cathode, reduction takes place. So this is a construction of Daniell or galvanic cell. So we can write the reactions. At anode, oxidation takes place. Zn gives rise to Zn2 plus 2 electrons. And at cathode, reduction takes place. Copper 2 plus 2 electrons gives rise to copper. So now we can write a redox reaction, overall net reaction as Zn plus copper 2 plus gives rise to Zn2 plus copper. Is a redox reaction. Zinc plus copper 2 plus gives rise to Zn2 plus copper. So whatever the electrons we have at anode, they start transferring from the zinc rod to the copper rod like this. So from the zinc here, it forms a Zn2 plus. Zn2 plus, it is mixed up with the zinc sulfate solution. And the two electrons which are liberated at anode, that are flow of electrons takes place from the anode of a zinc to the cathode, that is copper rod, where the deposition of copper takes place by copper 2 plus 2 electrons gives rise to copper. So this is the overall net reaction. Now we can have a representation of a cell representation of galvanic cell. So whatever we have done in the construction, anode cell, half cell is to be written on the left side. So that is Zn2 plus. You can mention here aqueous or the concentration. If it is 1 molar, then mention in brackets the concentration of the solution, and here double vertical line represents the salt bridge, and copper 2 plus copper sulfate whose concentration is to be mentioned either the aqueous or the 1 molar, and now which is immersed in copper, rod is immersed in copper sulfate. So this is the cell representation of a galvanic cell. So Nernst equation here. So we can apply Nernst equation for the above cell representation of that is zinc copper couple. So here E cell equal to E naught minus 2.303 RT N F log of Zn 2 plus concentration by copper 2 plus. So this is the Nernst equation. So now E cell can be written as E right side, that is copper, minus E left. So now we can apply E cell. E right side means copper 2 plus copper minus E Zn 2 plus minus 2.303 RT by NF log of 2 plus copper 2 plus. So this is a complete Nernst equation for the above zinc copper couple. Now, so EMF of a cell. So EMF of a cell is the difference between electrode potentials which causes flow of current from one electrode to another electrode. So the difference between electrode potentials is known as EMF. So next one is single electrode potential. Single electrode potential is, so here the potential difference between electrode and its corresponding salt is single electrode potential. So if we have, this is a cell, so this is a zinc rod immersed in Zn, immersed in ZnSO4, there will be the potential difference between the electrode immersed in its electrolytic medium. So that is called single electrode potential. And next, standard electrode potential value. Standard electrode potential. So standard electrode potential, the potential difference between electrode and its corresponding salt at particular conditions at 1 molar concentration and 298 Kelvin of temperature. So these are the standard electrode potential values represented by E naught. So E naught is equal to ER minus EL. So the values E cell is equal to E naught R minus E naught EL. So here we can have the numerical problems like on E M F. So calculate EMF for a cell Zn, Zn2 plus Ag plus Ag given E naught Zn2 plus Zn gives 0.762 volt. E naught Ag plus Ag gives rise to 0.8 volt. So we know already E naught cell equal to E naught R minus E naught L. So that is represented as right side E naught, that is E Ag plus Ag minus Zn, Zn2 plus. So substitute the values. 0.8 minus, so here minus 0.762 volt. So here in this Zn2 plus Zn given as 0.762. So E naught, what we need is Zn2 plus is minus 0.762 volt. So now after 0.8 plus 0.762, so we will be getting 6 to 1.5 volt. So it is a positive value. The reaction is feasible. So this is a one problem on EMF calculation. So today we have discussed introduction to electrochemistry, that is definition of electrochemistry, the branch of chemistry which deals with the interconversion of electrical and chemical energy. Cells are classified into two types. First one is electrolytic cell, second one is galvanic cell. And then conductor is the substance which conducts the electricity to pass through it. Conductance is the quantity or the amount or the tendency of conducting tendency to allow the electric current to pass through the substance. Conductors based on their electrical conductivity are classified into three types: conductors, insulators and semiconductors. So conductors are the substances which allows easily to allow the flow of electric current to pass through it. Semiconductors are the substances which conducts partially the flow of electric current, like silicon, which increases the electrical conductivity by doping with a third group element like a boron or a fifth group element like a phosphorus. Then non-conductors, those are insulators which do not conduct electricity, so their wood, plastics, etc. We have electrolytic conductors divided into three types. First one is strong electrolyte and weak electrolyte, then non-electrolyte. Strong electrolytes undergoes complete dissociation to give ions completely, and the partial dissociation takes place in the weak electrolytes like acetic acid and ammonium hydroxide. And then non-electrolytes, sugar in which the dissociation do not takes place even at a very high dilute solution. So those are known as non-electrolytes. Then we can discuss the galvanic cell in detail. Galvanic cell is the one which converts chemical energy into electrical energy. That is a decomposition of an electrolytic medium to release electrical energy. So in this process, production of electricity takes place. So we have seen the construction of electrochemical cell, which is consisting of two half cells. So two half cells, one half cell, this is known as oxidation half cell, and this one is reduction half cell. So oxidation half cell consists of a zinc rod immersed in its corresponding salt, that is ZnSO4, acting as anode or the negative electrode where oxidation takes place. And the reduction half cell consists of the copper rod which is immersed in copper sulfate solution, acts as a positive electrode or the cathode where the reduction takes place. So oxidation means loss of electrons from the Zn, which is giving Zn2+. The loss of electrons transferred from the zinc rod to the copper rod where the deposition of copper takes place in the reaction, that is copper 2+ plus 2 electrons gives rise to copper. So redox reaction here, it is Zn plus 2, Zn plus copper 2 plus gives rise to Zn2 plus copper. So this is the cell representation, and the Nernst equation is E cell equal to E naught minus 2.303 RT-NF log Zn2 plus concentration by copper 2 plus concentration. The concentration may vary, either it may be a 0.1, 0.01, 0.5 or 0.05. So E cell equal to E right side and E left side. So that is to be substituted depending on the oxidation and the reduction potential values. So E cell equal to E copper 2 plus copper and zinc 2 plus minus 2.303 RT-NF log Zn 2 plus by copper concentration. So here 2.303 and R is 8.314. Temperature can be a standard 298 Kelvin. Number of electrons may vary 1 or 2, and Faraday here it is 36500. If you 96,500, if you substitute all the values, then we get a 0.06 by N log of Zn2 plus concentration by copper 2 plus concentration. So here the EMF of a cell is the potential difference between the electrode potentials in both the half cells, that is oxidation and the reduction, where the flow of current takes place from one electrode to the another electrode. Single electrode potential, the potential difference between electrode and its corresponding salt, that is Zn rod immersed in its ZnSO4. The potential difference arises, that potential difference is known as single electrode potential. And the standard electrode potential is standard conditions where the potential value you have, that is called standard electrode potential. The concentration, if it is a 1 molar and the temperature is 298 Kelvin, then we'll represent it as a E naught, that is standard electrode potential. So we have the numerical problems in our syllabus on EMF of a cell. So here one cell have considered Zn and silver copper couple. So E naught, standard potential value of a Zn2 plus Zn gives as a 0.762. Here the value we have written as a minus because oxidation takes place. Zn2 plus, Zn gives rise to Zn2 plus and 2 electrons will be lost. So here the value becomes reverse with the negative minus 0.762, and the silver electrolytic medium, that is 0.8. If you substitute the values, we will be getting a positive EMF value, that is E naught cell is equal to 1.562 volt. That is a feasible reaction between Zn and silver. That means Zn loses its electrons, 2 electrons which are gained up by the silver to deposit the silver on the silver rod. So this is regarding EMF and the numerical problems on EMF. Thank you.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.